Sweet. All right, so I'm Finley McIlwaine. I'm a Haskell consultant at Well-Typed, and I'm just talking about advancements in info table profiling. So this talk's all about info table profiling. I'm going to talk about what it is, what's an info table, since I won't assume that everyone knows that, and then I'll talk about what are we profiling when I say info table profiling, why does this profiling method matter, and how do we use it, and then I'll talk about these advancements that we're making. And this is a lightning talk, so I'm going to go as fast as I can. So what is it? Well, to talk about info tables, we have to talk about closures, and I'll just define a closure as a static or dynamic object that represents a value or computation in your program, and these closures are described by info tables. And an info table is a static data structure that describes the layout of a closure in a way that the garbage collector cares about. Is a good way to think of it. So just as a simple example, every constructor of an algebraic data type will have its own info table that describes how the garbage collector can traverse that object when it's collecting it. So what is info table profiling? It's a memory profiling technique where we're tracking allocations in the program according to the info tables that correspond to the closures being allocated. So like every info table will have a count of how many bytes have been allocated just based on the closures that reference those info tables. And then when we use this GHC flag that you may have heard about, f-info-table map, when that flag is enabled, the code that gets emitted for a module will include provenance data for each of the info tables that originate from that module, which that provenance data is basically just a best guess source location for that info table and the type of the closures that it describes. And then when we use this other flag, f-distinct constructor tables, every usage of a data constructor will be given its own info table. So in the end, if you use those two flags, you end up with info table profiling, you're able to attribute allocations to info tables, and then with those flags, source locations. And if you're using distinct constructor tables, you're getting allocations at every use site of a data constructor, which is very useful. And this is a diagram that I put together that sort of just shows everything that I just said. If you go to closure X, its header is going to reference an info table at some address P in your compiled code. And then in the info table map, that address P is actually going to map to the provenance data for those closures. So why does this matter? Well, this profiling method has very high information to overhead ratio. You don't need to use GHC's profiling mode, so none of your dependencies need to be profiled. You can just profile exactly what you want and get this information. And it has a negligible impact on program performance. So just having the info table map in your compiled code won't affect your program performance at all. And when you're profiling, you get a very true look at how your program is acting. The profiling instrumentation is not doing anything to how your program behaves. And then this profiling method has excellent tooling support with tools like event log to HTML, where you can just turn GHC event logs, which are basically program traces, into interactive profiles. And then ghc-debug allows you to answer very low level and precise questions about how your program's memory is behaving. And for more on those tools, you can check out the Well-Typed YouTube channel, where we have a live streamed tutorial that I did for those tools, or our blog where we're always talking about these tools. So how do we use info table profiling? You need several GHC flags and runtime system flags. First, the GHC flags you need to compile with at least f-info table map, and then if you want the distinct constructor tables, you should use that as well, and most people do. Then you need to enable RTS options, and then for GHC less than 9.4, if you're going to be emitting an event log, you need to link with the event log flag. And for runtime system flags, you need to actually say that you want to do a heap profile by info table using -hi, and then you need to emit the event log using -l. So I'll do a very quick lightning demo. I have a program here where it makes a lot of thunks. And so in the GHC options, I do RTS ops. I say f-info table map. And for this example, it doesn't really matter, but I can say distinct constructor tables as well. If I run this and just say I want an event log and I want a heap profile by info table, then the Thunkinator 3000 will start running. And it won't take too long, but every time that these numbers print, the thunks are being evaluated, and so we'll get a very spiky profile that shows a bunch of thunks and then them going away. So then with tools like event log to HTML, you just run that on the event log, and then that generates an HTML file that I can open. If I just open that HTML file. This is what the profile looks like. A bunch of thunks being allocated and then evaluated. But in the detailed tab, I can see that these are thunks. The type of these closures are thunks, and they are integers, and they're coming from the main module at exactly line 23, column 18 to 24. And if I go and look at line 23, column 18 to 24, I'm obviously doing, I have a lazy accumulator here, and that's exactly where that thunk is coming from. So, yeah. Another thing to note is that I'm using a GHC that has the info table map in here, so I'm getting a bunch of source locations and things for things that are coming from GHC libraries. So that's why these are here. But if you run that without a GHC with the info table map, that won't be there. Okay, that's the Lightning demo. So what are these advancements? Well, producing the info table map used to be very inefficient, and on one particularly severe example, the flag caused whole compilation to take 130% longer and allocate 67% more memory. But this will be fixed in the next major release of GHC. And on the same example from above, whole compilation now only takes 13% longer and allocates only 10% more memory. And that's just an improvement that will be free to the users. And we're also working on making the binaries that contain the info table map smaller. And it gets especially large with distinct constructor tables because more info tables are being created and put into the info table map. But one observation is that the size of this info table map is often dominated by info tables that we don't necessarily care about for our profiling workflows. And so we're working on implementing features that allow users to filter exactly what tables get included in that info table map. And one of these flags that is now in GHC is this fno info table map with stack flag, which allows you to omit info tables for stack closures from the info table map. And often the info table map is dominated by info tables for stack closures because a lot of those get generated. And then also you can omit info tables that have defaulted provenance info. So if we can't figure out source location for these closures for an info table, then typically the source locations will get defaulted, but you can choose to omit those with this. And so just for example, I did some tests on the AGDA code base, but with info table map, it increased binary sizes for the AGDA code base by 36%, which is like 32 megabytes there. And then when you omit those tables with those flags, then the overhead goes down to 21%. So you go from 90 megabytes to 109 megabytes. So a small increase, but notable. And then, but when you use distinct constructor tables, the binary sizes are doubled on the AGDA code base. So distinct constructor tables introduces a lot of overhead. But we're changing distinct constructor tables to allow users to specify exactly which constructors this flag should apply to. So for example, you can say distinct constructor tables for only constructors that have this name. And that obviously erases the overhead of that flag and allows you to do very targeted profiling. And then also we're looking at adding, well, we've implemented a patch, but it's in progress, but we're working on doing distinct constructor tables per module, which causes only one info table to be generated for every usage of a data constructor in a module, which allows you to do like a sort of per module profiling. You can know how much this constructor is being allocated in this module, but you don't have to go so low as the exact source location of that usage. So yeah, it's just a more coarse-grained sort of distinct constructor tables profile. And that's all that I have, so thank you. Thanks to Hasura, who's the client that we've been working with that is funding this work on debugging information. And if you're interested in working with well-typed, please reach out to us. We'd love to work with you.